we're dealing with here when we have a uniform random variable is a variable that has equally likely continuous values between the random variable value of A and the random variable value of B. So it could be from 0 to 15. It could be from 1 year to 2 years. Whatever your entire range of possible values is, and as long as those are all likely events, then you have a uniform random variable. If you have a high likelihood of low values and a low likelihood of high values, like for example something looks more like this, then you wouldn't have a continuous random variable. That would be you would have a continuous random variable, just not a uniform continuous random variable. So to write a function for this, to write this what we call a probability density function, which we simply call PDF. And the probability density function, would not to be confused with the file type, by the way. Probability density function just tells you what the graph should look like if you have a uniform random variable. So if the variable is called capital X, then the function itself will look like this. It will be 1 over B minus A. So in other words, what you're doing is you're breaking this up, and you're breaking up the whole into B minus A components. In other words, if this interval is 10 units long, then you want each 1 unit interval to be 1 over 10. So this just allows us to be able to come up with a function for it and be able to plot it. The expected value, which I'm going to refer to as mu because really what we mean is average, the average of a uniform random variable is going to be A plus B over 2. So it's really just the average of the endpoints. So if your random variable goes from 0 to 5, then on average you would expect 0 plus 5 over 2, you would expect an average value of 2.5. In this case the median would also be 2.5 because it perfectly partitions the data in half. The standard deviation, which is what we're often interested in, is, well, it's obviously going to get bigger as the interval grows larger, so it's going to be dependent on the width of that interval, but, and this is the part where the intuition is kind of lost, you have to divide by the square root of 12. I know it seems random, but it's the end point minus the end point, the length of that divided by the square root of 12. So if B minus A is really wide, your standard deviation is going to be really big. So that's it for this continuous distribution. So let's say that you have x equals, and it doesn't have to be x, it could be whatever we want, like t is some sort of waiting time in minutes, and let's say that those times are, and we usually write it like this: the time is uniformly distributed, so this is distributed uniformly with A and B in parentheses. So A would be, let's say that waiting times range from 1 to 6 minutes. Okay, so that means that my function, which I'll just call f of t, would be 1 over 6 minus 1, which is 1/5, which is 0.2. So what this would look like graphically is from 1 all the way up to 6, I would have a constant function of 0.2. It would look like that, because it's 5 units wide. So the area, well, if this is 5 by 0.2, 5 times 0.2 is equal to 1. So that what this does is it guarantees that we get the full area of 100%. So this whole area is 1. And so now I can find probability. So the expected wait time would be, the mu, the expected wait time would be 1 plus 6 over 2, which is 7 over 2, which is 3.5 minutes on average. And my standard deviation would be 6 minus 1 over the square root of 12, which would be 5 over the square root of 12. And if we calculate 5 divided by the square root of 12, we should get about 1.4. So this comes out to about 1.4. So we could say, on average, you will wait between 3.5 minus 1.4 minutes and 3.5 plus 1.4 minutes. So pretty much the same interpretation as what we've dealt with in the past, except it relates to a different type of distribution. We won't use Chebyshev's